Let's start. Okay, let me bring up the slides. If you have questions or comments, this is now a good time to go over them. So let me also need to upload some more slides. Okay. Okay. No questions. Let me share my screen. Okay. So let's start with. Okay. So, or let's continue with the discussion last time. I guess I have to mute one of you guys. There is like background noise. If you have background noise, you can mute your microphone if you're not talking. Okay, so the last time we started talking about basically the main sort of result for the lasso, which is this theorem that says that if you have the RE condition, so recall again, we have this linear model or regression model, and the design is n by d, and d usually is much bigger than n. And so we assume that this theta star, the coefficient vector, is a sparse in the sense that the result doesn't require any assumption on S, but implicitly you're assuming that. So assume that this is supported on set S, and the cardinality of set S is bounded by little s, and then you have this RE constraint, restricted eigenvalue constraint over S. So X satisfies that, which basically means that over this cone, with alpha being 3, this lower bound holds for this quadratic form that's defined in terms of X. Okay. And we talked about why this is an example of a why this is an example of an eigenvalue. Why this is called an eigenvalue restricted eigenvalue condition. So this result that we have here is if you have this noise, modified noise vector, so X transpose W over N, and if your lambda is bigger than twice the infinity norm of that vector, then you have this bound for the lasso, which involves the lambda, and root S doesn't involve D, for example, directly. And this constant, which depends on the RE constant. We actually proved last time that a similar result holds for this constraint lasso. So instead of regularizing by the L1 norm, I add the L1 norm as a constraint. And I take R to be the L1 norm of theta star, so that theta star is feasible for that problem. Then what I would get is this result, which is similar to the so this bound, which is similar to the bound for the lasso. Instead of lambda, we get z infinity. So the two bounds are very close in a sense. up to their constants are a little bit different, but if you take the smallest lambda that's possible in this constraint, or so in this condition, then you get the same bounds. Okay.
I have one question.
Yeah.
Why do you introduce this variable lambda in the part A, and why not in B?
So that's part of the problem. So lambda. So this is.
Oh, I see. Okay. Oh,
Right. Regularized version of this.
Sorry.
Okay.
Sorry.
No problem.
Okay, thank you. Sorry. Yeah.
No problem. Yeah, it's good to remember what. Yeah. So the first one is about the regularized. The second one is the constraint version. So it has a parameter r, which is set it to be.
I see.
C
Okay.
star 1.
Okay.
Yeah. So this is not feasible though. Like in practice, you don't have this. But assume that you can take r to be large enough, such that you can see the bound does not depend on r directly. So
Yes.
this would hold even if I take r to be bigger than theta star L1 norm theta star. So there should be some price you pay. I'll let you go and figure out what happens if you increase this r. So there should be some price that you pay, but it is not quite visible from the bound. Okay. Okay. What do we have here? So this is the proof. Actually, this is the proof of the. It's a little bit messy, but this is the proof of. Let me just mention that we use this result to argue that. So this z infinity is the key point. So just remember that this z infinity is the only random quantity in this model, and this z infinity we argued that can be bounded like this, or you prove it in your homework problem, high probability, assuming this kind of normalization for the columns of x. And what you end up getting is once you plug the, let's say, choose the lambda this to be the smallest possible subject to this condition. Once you plug this in, you get that the L2 norm of the deviation is bounded by sigma root s log d over n, and then the log d is the price that you pay for this high dimensional search over all subsets effectively. Okay, so I hope people remember this. I'm not going to repeat this much, but the conclusion is quite important. So that's one of the interesting kind of non-trivial results about this high dimensional sparse regression. So the error is almost as good as if you knew the subset. The only drawback is that you have this log b factor, which cannot be improved. In any case, so we have the proof here is basically based on that idea of basic inequality. So we have written this. So this is for the constraint version. So you have written this loss function as or in this format, which is in terms of the deviation bound. So you have this, not the deviation of theta from theta star. So if I recall or call this quantity theta delta, then I can write the loss as a function of delta, which we did last time, and then the deviation, so the difference between the loss and at the particular theta hat and at the actual theta star, the difference can be written as you can see it here as this guy. Okay, where delta hat is so here delta hat is just theta hat minus theta star. So this side has to be less than or equal to 0 because theta star is feasible and theta hat is optimal. Theta hat makes L smaller. So this is less than 0 and then less than or equal to 0, and then if you rearrange, you get this so-called basic inequality. Okay, so we got this. We argued that if so this is the problem. This is the constraint problem. And so theta hat satisfies that constraint. And if theta hat satisfies that constraint, then what we get here is, so that if this satisfies this, we argue that delta hat should be in the cone, in that nice cone. And because delta hat is in that nice cone, we can bound the L1 norm of delta hat by a multiple root S times the L2 norm. So that was the key point. And there was a little bit of Holder inequality here, but once you do this, then you plug that back in here, and this side is lower bounded further by the L2 norm of delta hat squared up to this RE constant. And so this side, you have one of these, and the other side you have this squared, and one cancel out, and you get the result. Okay, so the key was to argue that delta hat is in the cone. Once delta hat is in the cone, then good things happen. So basically both, you get a good upper bound on this and a good lower bound on this by the RE condition, and then you can simplify and you get the result. Okay, any question about this? Was what we did last time. Does this make sense to people, more or less? I suppose it makes sense. So yes. Let's try to do this for a very similar argument. Let's not do it for the Lagrangian version, which is just Lasso. So here I have, I don't have the constraint, so I can't use, so in the constraint version, we use this constraint to show that the delta, the deviation is in that cone. Here we don't have that constraint, and so somehow the objective has to force the delta to lie in that cone, and that's sort of interesting. It's an interesting argument. Then. So let's do this. So now I define this new function, which is the L theta. The L theta was this previously defined loss function, right? So L theta is just the, let's say, the quadratic part of the loss. And so I have this plus the L1 penalty, so that's my new loss function. And so I just write down the basic inequality. So theta hat has to, theta hat is optimal, so minimizes this, whereas theta star is just a general. Theta star is definitely feasible because we're working on the entire RD. And so we have this inequality. Okay, that's our basic inequality. Again, if you recall, this is what I had before. So this side, this guy, is going to be 1/2n x delta hat squared minus z delta hat. And so I plug that, that's the calculation that we just did for last time we did it in terms of delta hat. You plug back in, and then you move this to the other side, you get this inequality. Okay, so sorry, this is not this, so this is basically, so this is L theta hat minus L theta star. Okay, so I rearrange. I basically move this to the other side and this other thing to the other side. Okay, and then this simplifies to this, and then I rearrange. So it's a little bit of rearrangement, basically. Okay, sounds good? Okay, let's say it sounds good.
Yes.
Right. So before we had just this, so we didn't have this part. Now we have this extra part. And now I'm going to do a little bit of manipulation. So this guy, you can see, is equal to, what I'm going to do is, I'm going to write, let's do this. So this is theta star plus delta hat. okay, and it's equal to theta star S plus, there's no S complement because that's the support, so I'm gonna not write it, plus delta S plus delta at S complement, okay? And so the L1 norm of this is gonna be equal to the L1 norm of this. Again, by decomposability, this is gonna be theta S plus delta hat S 1 plus delta hat S complement 1, right? And so I move this to the other side, right? And this is just theta S1 because there's no off support element here. So I move that to the other side and also this to the other side. So we get R, the equality, okay? And then the claim is that I have this inequality. So why do we have that inequality? How do we get that second line? So this is the same. This remains the same.
Triangle inequality?
Yes, so that's the triangle inequality. So going from this, we have done this multiple times. So this is, let me do a different color. So triangle. Okay, now, so I'm going to replace this. So lambda is positive. So if so I'm going to do a couple of things here. So it's a little crowded here. Okay, so what we have is 1 over 2n x delta hat squared less than or equal to z delta hat plus lambda times theta star 1 minus theta hat 1. Okay, so this one is bounded. Again, we're going to use the Holder inequality here on the first term. On the second term, I'm going to use the inequality that I just established. So this is going to be delta hat S1 minus delta hat S complement 1. Okay, that's the inequality that we have here. Now I'm going to use the assumption. So assumption. Assumption is that lambda is bigger than or equal to 2z infinity. Okay, and you'll see why there's a 2 there. So now I have, this is bounded by, I'm going to bound it by lambda over 2 basically, times this plus the rest. Okay, and then multiply both sides by 2. We get 1 over 2n, no 2. This is x delta hat squared less than or equal to lambda delta hat 1 plus lambda, yeah, 2 lambda here. Multiply everything by 2. Okay, minus. Okay, so now we have this. So now let me ask you, what do you think we should do next? So I have this nice inequality.
Decompose lambda hat as lambda hat s plus lambda hat s complement.
Good, yes. So this is going to be decomposable. So I get this plus the L1 norm of S complement. Okay. And there's a lambda behind it.
Yeah.
So next, what happens?
You'll have 3 lambda delta hat S.
3 lambda delta hat S 1 and minus lambda
Oh yeah, you will have 1 minus, yeah.
delta hat S complement 1.
Yeah.
Right?
Yes.
Okay, now what is the
Use
next
the
step?
definition of this C alpha of this set.
So I'm
Right.
going to recall C, let's say 3 of S
Yeah.
is sort of all deltas in our D such that delta S1 is less than 3 times delta S complement 1. So what
Or
can
you
we
mean,
say now?
or is that delta S complement?
Yes, the other way, right. It should be S complement 3S. Yes, the bad part, which is off support, is controlled by the good part, which is the on support.
Yeah.
So now, what can we conclude?
I mean, this is bigger than.
So yeah, the inequality is that this is bigger than this. So that's my inequality. So what does this tell us about delta hat? I know that lambda is also positive. Anyone has a guess? Can I conclude that delta hat belongs to this cone? I'm going to say yes. Why can I conclude that delta hat belongs to this cone at this point? So there's something that implies that delta hat belongs to C3 of S. What is that little argument then?
Well, C3 of S is the set of deltas where this like right-hand side in our boxed inequality is positive, and we know it's positive. I guess you have to divide by lambda.
Right, that doesn't matter. So this is non-negative, right? Then you can divide by lambda, yes. Yeah, so because it's a cone, it just, if delta hat belongs to it, then lambda times delta hat belongs, yes. So, but the basic idea is that this is non-negative. Okay, and that statement, this implies this. So if you set this side to be non-negative and then cancel out lambda and rearrange, you can see. Yes. So you can see the basic inequality forces. So basic inequality forces delta hat to belong to the good cone. Which is an interesting or impressive result if you think about it. So we did not impose this constraint, but at the optimal solution, the optimization forces this constraint on delta hat. Okay. Optimization problem itself poses this constraint. We did not explicitly impose this. Okay, so now I'm good because what is the next step then? So I can use the RE condition, right? That's one of the things that I can do. So what should I do here? the next step. I'm going to use on the other side, this side, I'm going to use the RE condition. So this is going to be bigger than or equal to kappa times delta hat squared. Okay. RE condition. And the other side, I'm just going to drop that second term now. I don't need it anymore. So I'm just going to get an upper bound. So just drop this. You get an upper bound. So what next? Okay, so we get kappa delta hat squared is less than 3 lambda delta hat S1. Right? So can I bound this by the L2 norm?
Yes.
What kind of bound do I get?
Root S time.
Right. Y root S? Rho S, this should be big S. Y root S?
I mean, that's what it gives by Cauchy-Schwarz.
Right, so delta hat S is in
It
R
is
rho S.
S components. Yes, yes.
So,
It is
and
S
then this
component.
is, yes, and this is bounded by, so these are big S, one of them are big S, I can't write both. So this is big, this is, the other one is little S.
Yes.
So, let me try better. So this is little s, this is big S. So I get root S also bounded by the delta L2 now, right? Why?
I mean, delta is more components.
Yeah, so it's easy to verify that that's exactly true. Okay. Now I have, what do I get? I get kappa delta hat 2 less than root S delta hat 2. From this you conclude that delta hat 2 is less than or equal to,
You
sorry,
have 3
that's
lambda.
3. Yes, I get 3 lambda root S. Less than or equal to 3 lambda root S. So I get 3 lambda root S divided by kappa, which is the result that we wanted to show. Okay, so this delta hat is, this is just theta star, or theta hat minus theta star. Okay, done. QED. Okay. That's what we set to show. So the proof is a little bit trickier than the constraint case, but the idea is the same. So you basically start with the basic inequality, which comes from optimality, like zeroth order optimality condition. And then you manipulate it, you get an inequality which forces, use Holder inequality here, the assumption on lambda, and you can see why we need lambda over 2 here, because I need something which is smaller than lambda, right? Because I would like to sort of get a negative here. You could have done different values, but your cone, the 3 would be different. But if you think about it, you can see lambda over 2 is a good choice. And you do this, and you end up with this cone, this inequality which forces this cone condition, and then you get the rest of the argument follows as before. Okay, the key is that the L1 norm of this little piece appears on the other side, which is small relative to the L2 norm of the, or L1 norm of the full vector. Okay. It's a nice argument, and it's not that obvious, but it's not difficult either. So to prove an interesting result with this fairly a straightforward argument. So, you know, have any questions about this? Okay, so we now have all the pieces of this result except, so we have proven this result. We also seen how you can get, or you can show it in your, you will show it in your homework problems, how you get from this result to this basically explicit bounds on the error when the noise is sorry, when the noise is a Gaussian or sub-Gaussian. Actually, it's enough to be sub-Gaussian with independent entries. What we haven't shown is, or we haven't verified or talked about much, is when this RE condition holds. And that's basically the difficult part of this. So it's a strong condition, and in general, it's hard to verify because you have to, it's a uniform condition. So you have to say this is uniformly lower bounded for all delta. And this is not all delta in this cone. And this is not in general easy. For example, if this wasn't there, in order to verify this, you had to find the minimum eigenvalue of X transpose X, which is not an obvious calculation. So there is some computation. And you can imagine this problem is going to be harder. And the problem is not, for example, convex. So you can't solve this as an optimization problem. I can't say I divide by the L2 norm here and then minimize over all the deltas. The cone is convex, but the constraint that, the objective that you get is not. So, for example, I can try to see, minimize 1 over n x delta squared divided by delta over delta in C alpha of S. Okay, so not a convex problem. So this problem in general is not easy to solve. One thing that you can try to, for example, as a project, you can go see whether there is any new developments on trying to verify. Especially this is going to be difficult if you have a given, if you're given a particular design matrix and you want to verify whether that particular design matrix satisfies this. I don't know of any good way of doing it in general for a general matrix. Okay.
Why is this not a convex problem? I mean, you can consider all the deltas with non-1, and then it is just a square of the entries, right?
You can do norm 1, but norm 1 with the constraint would be, yes, I can sort of, for example, I can sort of do this and set the L2 norm of this equal to 1, but then the constraint set is not going to be convex.
I see. Okay.
Right. It's a tricky business. Yeah, this is a hard problem to solve. And yeah, it's a good research topic. Is it possible to verify it in polynomial time in, for a given x, for any x? But what people have done instead is that they have shown that for random design matrices, so matrices that are randomly drawn, this condition holds with high probability, which is reassuring. It's not something that cannot be satisfied. So there are many matrices that satisfy this, and this is a particular result that's in the book, and it's somewhat general. So so the result is saying this. So if you have a matrix X n by d, and the rows are drawn from a multivariate normal family. So I have this is n by d, and each row, so this is drawn from a normal with mean 0 and covariance sigma. So there is correlation among the elements inside inside this row. But then the rows are independent. So the rows are IID draws, but the elements within the row are correlated. Then there are universal constants such that this inequality holds for all theta, basically. Or you can imagine theta being delta.
So you are saying that this statement holds for all theta in R to the D, so which is an unbounded set.
Yes.
R to the
that's
D.
True.
I see.
Yes, so this is an interesting result, and this holds with this probability, which is quite large. So as n gets to infinity, this probability going to 0 exponentially fast, to 1 exponentially fast.
So I just one thought. Here, since this theorem holds for all theta, which is in RD, which is an unbounded set. In general, when you prove this kind of statement, you need to apply some covering argument, right? But then those only holds for a bounded set because you cannot cover.
Yes, it's a good point. This is the proof of this is tricky, and it's in the book. I'm not going to prove this. We'll see. If we have time, I might come back and try to prove this, or you guys could present it. You're right. So whenever you see some uniform bound like this, someone claims this, the argument generally is interesting. Sometimes it's easy, but sometimes it's not. For example, if I say, I'm going to unpack what this means shortly, but because you asked. So for example, if I want to show, I don't know why this doesn't work. Sorry, let me try to see if I can open. This is very weird. What happens if I open the page here? Okay, it's going to do the other side. Down here. It's going to go. Okay, it's okay. So let's say I do want to show that x, let's say theta squared is bigger than or equal to kappa theta squared. Okay.
Mm-hmm.
For any theta in RD, this seems to be a result that hold on an unbounded set, but you can equally argue that it's enough to show that x theta, for example, squared is bigger than or equal to kappa for all theta in RD such that norm theta is 1.
I see.
Right.
Okay, good. Okay, got
Right.
it.
But this is still problematic because this is not a finite set. So you need covering ideas or something like that.
Yeah, but it's a bounded set, so you can use epsilon net arguments to.
Yes, you could do that. We'll talk about that. Yes. A similar idea goes here. So you can see there are 2 parts. So this is the tricky part. This is the meat of the thing. So what I can't do, the idea is that what I would like to have is this bound. So I wanted to have this lower bounded by this guy. But this can't hold over all RD. So we're going to pay a penalty. This is a non-negative penalty. And if this is sufficiently big, it makes the right-hand side negative. And so the bound trivially holds. Okay. the idea is that for some thetas, this is going to be much smaller than this, so we have a non-trivial bound. Okay, so that's the penalty we pay for trying to achieve something which is which shouldn't hold in general. So let's try to understand this condition a little bit better. So first, so if you want to show something like this, your first guess would be to try to see what the expectation of this side is. So this is a random quantity. I would say that if I'm lucky, I'm going to show that this side is basically concentrating near the expectation. Okay, and so what is the, what is that? So what is expectation of x theta squared over n? How do we compute this? So x has IID rows from normal 0 sigma. So this would be 1 over n, right? I can write it as theta transpose x theta, and I can put the expectation here, if you agree with me. Okay. So what is x transpose? So if x is,
It's a summation of xi transpose.
right, if I write x like this, then x transpose would be x1, x1, say x2, xn, and so x transpose, is that so?
Yes, so I think, yeah, x transpose x is summation of xi transpose.
Right, you get some I from 1 to n. Yeah, so this is d by 1. This is 1 by d. So when you multiply out, you get the summation of these. So verify that this is correct. So 1 over n would be 1 over n. Oh, sorry. Okay, so this I can define as sigma hat n. This is the sample covariance matrix for this data. Sample covariance matrix based on xi. Okay, so what is the expectation of sigma hat n?
Yes, covariance of whatever the rows are taken.
Right, so it would be just sigma. Okay, so I get that this is going to be theta hat sigma theta. Okay. In other words, what I can write is that expectation of this x theta over n is just norm of root sigma. Okay, this is the symmetric square root of the matrix times theta squared. Okay. So this piece that I have here is basically the expectation of the left-hand side. And you would hope that this is close to its expectation. So for any fixed theta, this is going to be close because why can we say that for any fixed theta, this is going to be close?
Sorry, I didn't get. What did you ask? I didn't get.
This guy, for any fixed theta, what I want to say is that x theta. So you can verify this. So this we can write as basically theta transpose sigma hat n theta, which is 1 over n summation theta hat. This, you can write it this way. Okay, so this, by the law of large number, converges to the expectation. which is just this other side. Right, so for any fixed theta, this is close to that. The problem is that we want it to be uniform in theta. And then there's, and also we want a quantitative bound, like non-asymptotic bound. And so there's a price you're going to pay. And that's the price. So that's the price that you're going to pay, because you don't, you can't have it over all theta. That's one way of writing it. To see why we can't have this, that this holds for all theta. What can I say? I just drop this part, and this will hold for all theta. So here I'm assuming that sigma is non-singular. So are there theta such that this is 0 and this is non-zero? That's the easiest way. Let's see. So x, so generally, let's say d is much bigger than n. So x has a non-trivial kernel. So any theta in the kernel of x is going to make this side 0. But this is going to be always non-zero if theta is non-zero. Okay, because sigma is assumed to be non-singular. So this is the population version, which is well-defined and non-degenerate, but this quadratic form is degenerate. So I can have this in high-dimensional case. If things are low-dimensional, then I can. But if things are high-dimensional, then we can't do it. So that's where the role of the other one. So now to see why, so this is, this quantity is the maximum diagonal entries of sigma. And to see why this inequality is interesting, I'm gonna do this. So we further lower bound this part. We can lower bound this by the minimum eigenvalue of sigma times theta del 2 normal theta squared. So the minimum eigenvalue, this is the notation of the book for the minimum eigenvalue. Okay, so why this equation is, or why this inequality is correct?
By definition, I guess.
Right, but by the property of the minimal eigenvalue, this is the Rayleigh-Reeds, or these variational characterization eigenvalue. So this you can verify for yourself that this is going to be bounded by the minimum eigenvalue for all theta in RD. Bounded below. Okay, so what this is saying is something like the RE condition. This is like the RE condition, but for the population covariance matrix. And in fact, it's not restricted. So this is a minimum eigenvalue condition. Okay, so this holds for the population covariance matrix. Now, if I plug this in here, let me see what I've defined here. So I would like to, so why this is interesting. So what I have is x, let's say that bound holds bigger than or equal to C1. Let's see what I called this here. Okay, so I'm gonna lower bound this. So let's lower bound this further by C1 gamma min sigma theta at 2. So I have C1 gamma min theta hat 2 gamma min of sigma minus C2 rho squared sigma log D over N theta 1 squared. Okay, so that's the bound. I'm going to call this, I believe, alpha 2. Let's see. And this is alpha 1 for simplicity. So these are known parameters. So what I have is this bound is like this, bigger than or equal to alpha 1 theta 2 minus alpha 2 theta 1 squared. Okay, so so this bound is going to be good for vectors whose L1 norm is much less than L2 norm. If the L2 norm is close to the L1 norm, then things are not necessarily that good. But what are the vectors whose L1 norm is potentially smaller than the L2 norm? And that can be a smaller, but the L1 norm is smaller compared to the worst case that it can be relative to the L2 norm. So L1 norm generally is bigger than the L2 norm. But what are the vectors for which the L1 norm is controlled?
Sparse vectors?
Sorry?
Sparse vectors, maybe?
Yes, for sparse vectors you've seen. So if theta is, so if, let me see if I can open another page here. Okay, so if theta is S sparse, right, then I would have that this guy is bounded by root S theta 2. Okay, sorry, this you've seen, right? So if this is S sparse, then only there are only S non-zero entries. So I can restrict to the support, and I get, instead of getting root D here, I get root S. And then I plug back in, I get x theta 2 over n bigger than alpha. Theta 2 minus alpha 2 root S, or sorry, S squared. Right, theta 2. Okay, so if alpha 1 is bigger than, let's say alpha 2s is less than 1/2 alpha 1, then I get x theta 2 where n is bigger than or equal to 1/2 alpha 1. This for all S is sparse theta, which is a form of RE condition. It's not on that cone, but it's sort of, you have some sort of a uniform lower bound for all S is sparse theta in RD. Okay, that's the idea. And this condition that we have here, let's color it something else. This condition would be equivalent to, so alpha 1 is, so alpha 2 is C2 rho 2 sigma log D over N, and the other side would be less than or equal to 1/2 C1 gamma min sigma. So this is saying times S. That's alpha 2 times S. Oh, sorry, the other one. S times this. Okay. Right. So this is saying as long as S log D over N is less than or equal to this constant.
What is rho?
Rho is this guy, the maximum diagonal entry of sigma.
Okay.
So as long as this holds, which is, let's say, generally going to be true if this side is going to 0, which is what we would like to have, because this other side is constant. then I would have this RE condition. So this is, or another way of doing it is, you can say that S should be bounded by, or let's say S should be bounded by that thing, this thing here, times n over log d. Okay, S can grow like this, or you can say that n should be bigger than 1 over 1/2 C1 gamma min sigma over this times S log d. Okay, so you can see there is this type of sample complexity condition. So you can think of this part as a constant. So as long as n is bigger than or equal to up to a constant, which depends on sigma, S log d, then we have this, let's say RE condition for the sparse vectors. Okay.
And sigma.
You can also, so yeah, is there a question here?
And sigma is what? It's a covariance matrix of.
Yes, the rows of this. So what I've shown here is that if this condition holds, if this holds, then you have an RE type condition like this for all S sparse theta. So it's not on that cone, but on S sparse theta. So it's a uniform on over all thetas that are S sparse. This holds, and for this to hold from that condition, you need a condition like this. So you need a sample complexity like this. So this is saying as long as n is bigger than or equal to S log d, then you're good. Sigma is fixed, so more or less. Sigma is growing, but so I'm going to give you examples. So sigma also could grow because it's d-dimensional, but the minimum eigenvalue and this maximum diagonal entry could be fixed. Okay. Right, and then similar argument, this is an exercise for you. You can do the same idea, that the same approach that I did. From this condition, conclude that the RE condition holds over this cone, which is a little bit different than the S sparse vectors. If you have this kind of, the cardinality of the set is bounded by the same thing that I mentioned. So some constant divided by n over log d. Okay, it's similar to this condition that I have here. So this you do as an exercise. So basically this type of uniform bound gives you the RE condition for subsets that are not too big. Okay. In other words, if n is bigger than or equal to S log d, then the RE condition holds for all subsets S of cardinality less than small s. Okay. And this is the conclusion that I mentioned at some point that we are going to sort of show. So remember, this was the thing that I mentioned. So if n is bigger than S log, this is a little better, S log d over S, but let's say S log d, then the basis pursuit succeeds. Basically, this condition if it's satisfied, then you can verify that the restricted eigenvalue condition holds. For this sigma, we'll see it. For this sigma, it's those parameters that I mentioned, gamma min and rho, are constants. So if the RE condition holds, then the null space, restricted null space condition, which is a weaker condition, holds, and if that holds, then the basis pursues succeeds. Okay, that's the sort of idea here. Okay, I get my battery died again. So let's go back to this. I'm going to talk about that later. Any question about this sort of result? Does it make sense to people? This is not an obvious result. This is not easy to prove as well. But what I'm just saying is that if you have something like this, then you'd get the RA condition. How to prove something like this is a little bit tricky, but just wanted to point out that this is an interesting condition and stronger than the RA condition. So, and then Gaussian matrices satisfy this with independent rows. So let me show you an example. That's the example that we did. So this, suppose that rho is the sigma is a top-place matrix. So sigma is like this. So it's 1 nu squared, and then 1 on the diagonal. Nu is here, nu squares all the way here. So this is a top-place matrix. So things would vary along the diagonals. Okay. Different things happen. And if you have a top-place matrix, then anyone knows what kind of objects or what kind of models give you top-place covariance matrices?
It's the ones where you have like time steps that depend. What are those called? It's like you get those recursive definitions of each time step.
Right. So you have like AR models for an AR model, for example, for a time series would do this.
Right.
So this saying that the correlation basically for time series this happens. The correlation, let's say nu is less than 1. So the correlation exponentially dies down as you increase lag. So this is, for example, the correlation between the first guy and itself, the first time. This is the correlation between the first guy and this, like, its past. And you can think of this as this is the correlation between the ith time and the jth time. And as the time passes, the correlation exponentially dies down. Yes, time series are a good example. So you can see the maximum diagonal element is 1, and it's also possible to show that the eigenvalue, minimum eigenvalue is 1 minus nu squared, which is positive, strictly positive. So, and you can see that they don't depend on the dimension. So this is d by d, and these parameters are dimension independent. So this part of the constant is constant. So C1 is a numerical constant, and lambda min is 1 minus nu squared, and rho is 1. Another example is this one that we saw in the basis pursuit. So 1 on the diagonal and mu everywhere else. So again, this is 1, and the lambda min we calculate to be 1 minus mu. And you can see in both cases, the condition just reduces to something like this, where the constant just depends on this parameters mu and mu. Okay, and this was the case where we discussed about the basis pursuit being consistent, even though RIP conditions or pairwise invariance fails. So, for example, what this result is showing is that for those covariance matrices, although RIP and pairwise invariance fails, this result gives you the restricted eigenvalue condition, hence the restricted null space condition, hence the proves that basis pursuit succeeds for these type of covariance matrices. Okay. Questions, comments? No questions? Okay, so in the remaining time, there are a little bit more, not a little bit, there are other results in this chapter, which, so I used to go over some of them in more detail, but in the interest of time, I'm gonna skim over them, and then you can pick up and talk about them if you want. So that was the basic sort of argument. So except for this theorem, which is proved very differently, the next one, the oracle one, and the another theorem after that are proven using the same basic idea. So this result, which is called Lasso's oracle inequality in the book, is basically the same type of result, but without assuming any sparsity for theta star. Okay, so this is saying the Lagrangian Lasso with this regularizer, the same condition. If you apply it, and no matter, go
Can
ahead.
you please zoom in a little bit? This is, yeah.
Okay,
Thank
so
you.
this is saying if you do this, oh, sorry. This did not work as intended. Okay. Right, if you apply to theta star, so before we assume, so no assumption, so this no assumption about the sparsity of theta star. Okay, so the difference between this and the previous result is that we do not assume any sparsity for theta star, so just apply this result and you get this bound, which this part of the bound is similar to, and this bound holds for any S, any subset S of this cardinality, the cardinality of most S. So you pick some subset S with this cardinality, and then you have this bound, okay? And because you have this, then you can go and choose the best S to minimize this bound, okay? So this has two parts. There's this estimation error part, which is similar to what we had before. So before we had theta hat minus theta star 2 is less than 3 over kappa root S lambda. So if you square it, you get theta hat minus theta star squared is less than 9 over kappa squared S lambda squared. So that's this part of the bound. So this is very similar to this. So here kappa bar is basically lambda. So this result is under this condition, the condition that's here. So this is the sort of, this condition is very interesting. So if you have something like this, then you can prove that oracle type inequality. So assuming that this holds, which is the strong result, which holds for the Gaussian matrices. So if you have this star, that's this condition which is not showing. Then with kappa bar being the lambda mean for simplicity, and rho squared being the what defined there. So you get this first term, which is the estimation error. This is the error due to noise. And then you get some extra terms, which the book calls approximation error. And this is the error that you incur because theta star may not be sparse. And so you can see the off support part of theta star comes in. So here S is not the support of theta star, so S is a general set that you take. And you can try to minimize. So you can try to minimize the contribution of this term. So, but that's what the result is. So if you apply that condition, and then you go to a similar argument that we went through in the first theorem, then you get this result. Okay, so is the statement more or less clear, or the difference between the previous result clear? There's little intuition that I can give about this. It just follows from, the only intuition is that there are two pieces of information. So if, for example, theta star was a sparse, you could take S to be its support, and then this part would go away, and you get back the original. If theta star is not a sparse, there's like the support is everything. You may still choose S in this result such that this is small, so you don't pay that much of it. like extra cost or extra price. Does it roughly make sense? Or no? No comment. Well,
So
yeah.
what was the earlier bound when you had this restriction of the on the S?
What, can you say that again?
And what was that bound earlier that you proved when you have a restriction on the support? What was that bound?
So the bound was this.
I just wanted to see whether that. Okay, I see. So you have a square there, and
No, so I just mentioned, so you can square. So this is it wasn't this, the first bound was like this.
I see.
Okay. And if you square
Oh,
it, you get
okay.
something like this, okay, which would look like this, because this is about
Which is
theta
yeah.
squared. So that first term is exactly, more or less, not exactly. So here we are not directly assuming the RE condition, we're assuming this star, which is a little bit stronger. And so the RE constant, we're getting this kappa squared, which is just this guy. But these play the similar roles, okay? The idea is that this first term is basically the term that we had before. Okay, lambda squared S divided by kappa squared. Okay, let me show you what this could give you. So the idea is that this bound can be optimized. So you can try to balance all these terms, or minimize basically. In order to make sense of it, I'm going to simplify. So the key components here are first this guy and also lambda. Okay, we care about these. This part and this part, the rest are constants. I'm going to shove them into constant. So what I would get is this, right, times a constant, this guy times this, times a constant, and lambda squared times s. Okay, so if you go through this bound and then do throw away the constants, call them kappa 1, kappa 2, kappa 3, you get something like this. So that's the nature of the bound. And there should be a sigma squared somewhere. So sigma squared is appearing in choosing the lambda. So suppose sigma squared is 1. Then from the previous discussion, we know that z infinity is roughly root log d over n. This is what we have. Or you prove that with high probability this is the case. Then I can take lambda to be of this order. Lambda has to be bigger than the constant times z infinity. So I just take lambda to be basically of the order up to constant root log d over n. Okay, that's the choice that I'm going to make. Over n, all under the square root. Well, we're out of time actually, so let me very quickly. Actually, I can't do it quickly. So if you do the lambda, then what would you get? You get this, and you get root lambda here. Sorry, you get lambda squared. So this is lambda squared, and you get this. And then what you do is you can write down, and then this is again a constant. So the cardinality has to be less than n over log d. So you'd get this result. So you'd optimize over all s such that this holds. And this is why this is called, this is the bound that you get. This is called an oracle, because one of the reasons, there are multiple things that called oracle inequalities. I guess different things people call oracle inequality, but this is called oracle inequality because an oracle who knows theta star can solve this optimization problem and get the best bound. You, on the other hand, might not be able to solve it because you don't know theta star, you don't know which S you can pick, but if you knew somehow theta star, then you could get the best bound. Okay. Next time, we're going to come and do one example how to do this for the L cube sparsity. So this result, for example, gives you a nice bound when you assume that theta star is in the L cube ball. It turns out that you don't need to know the exact theta star. You just need to know that it's in the L cube ball, and then this bound simplifies. You get a nice result. Okay. Questions, comments? Yeah, this result is a little bit tricky because I haven't proven the star, and I'm also not going to prove this. But the proof of this is quite straightforward, similar to what we did before. You just replace the RE condition with this new condition, and also you don't have the the support of theta star is S, so you can't get rid of theta star as complement, but you have to do a little bit of manipulation. I have a proof here, down here, compact version. You can read this if you want. And if you have questions, you can go over them. This is basically a compact version that you can try to unpack yourself and see if you understood these arguments. And you should be able to prove this. Okay? Questions, comments? Okay, if no questions, then thank you for listening, and hopefully catch you offline.